Welcome to this explainer. Today, we are taking a seriously cool mathematical journey. Starting from the concrete, physical tiles of a beautiful Spanish palace, all the way to dynamic, digital proofs right on our computer screens. We're going to uncover how we actually do mathematical investigations. How we move from just looking at a single, real-world example to discovering a universal, ironclad algebraic rule that works every single time. Here's our roadmap for today. First, we'll tackle the Alhambra tile puzzle. Next, we'll look at spacing out wall tiles. After that, we'll dive into dynamic triangles using ICT. And finally, we'll wrap up by proving some circle angle theorems. Let's jump in. Section 1, the Alhambra tile puzzle, where we'll be generalizing physical geometry.
Okay, so if you've ever had the chance to see the Alhambra Palace in Spain, you know it's absolutely famous for these stunning fountain pools surrounded by intricate ceramic tiles. But as mathematicians, we don't just admire the view, right? We look for the underlying structure. If we look at one specific pool, sure, we can just count the tiles, but how do we calculate the exact number of square tiles needed to surround literally any pool of a similar shape, no matter how big or small it is? How do we take a physical space and translate it into a reliable mathematical formula?
Well, to find a general rule, we always have to start with a highly specific, concrete example. So I want you to imagine a rectangular pool that is exactly 11 units long and 6 units wide. But it's not a perfect rectangle. A square of exactly 2 by 2 units is cut out from each of its 4 corners. If you're picturing it, it looks a bit like a thick plus sign, or maybe a cross. Now, if you were to literally get down on your hands and knees and physically lay unit square tiles around the border of this exact 11 by 6 pool, you'd find that it requires exactly 38 unit square tiles. 38. And hey, thankfully, we don't have to glue them all down ourselves, but this gives us our perfect baseline, a rock-solid, undeniable fact from which we can start hunting for that underlying rule. So how do we move from that one specific fact to a universal truth? We get organized. We investigate different sized pools and log our results in a simple table. We'll use variables here: m for the pool length, n for the pool width, and x for that little corner cut dimension. By testing out different pools and filling in the total tiles, which we're going to call t, we can begin to spot the pattern. And from these recorded results, we can eventually write out an algebraic rule using m, n, and x to calculate t for a pool of any size. It's like solving a giant puzzle. Moving right along to Section 2, spacing out wall tiles. Let's see how we deduce formulas from grids. Building on that exact same investigative logic, let's look at a vertical surface, tiling a wall. If you've ever watched a professional put tiles on a wall, you know it takes incredible skill to keep everything perfectly aligned. To do this, they use these tiny plastic pieces called spacers. But notice the geometry at play here. There are cross-shaped or plus spacers used on the inside of the pattern, exactly where 4 interior tiles meet. And then there are T-shaped spacers, and those are used right at the outer edges of the tile pattern. So different physical locations on the wall literally require different geometric shapes. Just like we did with the Alhambra pool, if we want to know exactly how many of each spacer we're going to need for a whole wall, we methodically sketch out different sized rectangles, some L tiles long and W tiles wide. We count up the plus spacers, let's assign that the variable C, and we count the T spacers, variable T, and we drop them into an ordered table. By carefully changing the length and width and tracking the changes, we can actually deduce 2 completely separate algebraic formulas, one for C and one for T. Again, it all comes down to structured observation. All right, on to Section 3, dynamic triangles in ICT, visualizing similar triangles digitally. Up until now, we've been working with static geometry, tiles physically glued down to a floor or a wall. But now, we're going dynamic. We're bringing in ICT, which stands for Information and Communication Technology. By firing up dynamic geometry packages like Cabri or GeoGebra, we aren't just sketching static shapes on a piece of paper. We're constructing them digitally. This completely changes the game, allowing us to manipulate the geometry in real time, bringing the math to life right before our eyes. Okay, picture doing this on your screen right now. Step 1. You use the software tools to construct a basic triangle, and let's name the vertices A, B, and C. Next, you construct a new line segment inside it, let's call it ED, making sure it cuts across the triangle but is strictly parallel to the bottom base, AB. Then, you use the digital measurement tool to instantly find the exact lengths of all these new line segments. And finally, step 4, you pull up the built-in calculator tool to find their ratios. So the real magic here happens when we focus on what the software outputs for us. We're not just staring at random numbers. We are deliberately calculating and comparing the ratios of corresponding sides. We look at the big base AB divided by the small parallel base ED, then the long side AC divided by the shorter section EC, and finally the other long side BC divided by DC. When you do this, you'll notice something absolutely incredible. All those ratios are perfectly equal. Boom. You've just visualized similar triangles. But here is where this software becomes an absolute game changer. Think about it for a second. What happens to those calculated ratios when you literally grab a vertex, say B, A, or C with your mouse, and just drag it to a completely new random position on the screen? Or what if you grab point D and slide it up and down the side of the triangle? Because of the geometric rules hard-coded into the software, line ED stays perfectly parallel to AB. And as you watch those numbers spinning in real time on the calculator tool, you realize the ratios stay perfectly equal, no matter what. You aren't just proving this for one static triangle, you're proving it for an infinite number of triangles all at once. Which brings us beautifully into Section 4, Proving Circle Angle Theorems. Let's unlock some circular geometry. This crazy power of dynamic digital tools takes us straight into our final challenge. But before we dive into the actual theorems, let's quickly define a really crucial term so you're totally up to speed. A subtended angle is simply an angle formed by two lines that originate from the two endpoints of an arc on a circle. Think of it like a slice of pizza. You start from the two ends of the crust, and they meet at a point in the middle. The angle at that pointy end is subtended by the crust. Make sense? And let's lock in one more key definition to make sure we're perfectly clear before the final reveal. A cyclic quadrilateral is just a four-sided shape, a polygon, where all four of its corners, its vertices, sit exactly on the outer edge, the circumference of a single circle. That's it. All right, now using our dynamic geometry software, we can draw a circle and instantly visually demonstrate three incredibly profound properties. First, the angle subtended at the center of a circle by an arc is exactly twice the size of the angle on the circumference subtended by that same arc. You can drag the points all over the screen, and that 2-to-1 ratio literally never breaks. Second, angles in the same segment of a circle are always equal. And third, if you draw out one of those cyclic quadrilaterals we just talked about, you'll see that its exterior angle is always exactly equal to the interior opposite angle. Instead of writing pages and pages of tedious proofs, the software lets us literally see the truth of the geometry as we play with the shapes. We've gone all the way from counting physical, concrete tiles around a pool in Spain to dynamically proving deep geometric theorems with just the drag of a mouse. By observing, recording, and using the right tools, we can uncover the hidden rules of shapes. Which leaves us with one final, pretty amazing thought. If our digital tools can instantly prove these ancient rules, what totally undiscovered mathematical patterns are hiding in the spaces around us right now, just waiting for us to investigate? Thanks so much for joining me on this explainer, and definitely keep looking for those patterns.